Today we're going to finish section 10.3 and do a couple more examples in this video. In this problem, we're going to do a two-column proof. We're told that the arc AB is congruent to arc DB. So if we look in the diagram here, we have arc AB congruent to arc DB. That's our given. We want to prove that angle ABC is congruent to angle DBC. We'll start off with information about the arcs, but we can use that to talk about the sides of this triangle. We have a theorem that says in a circle or congruent circles, congruent chords or congruent arcs have congruent chords, and also congruent chords have congruent arcs. In this case, we want to say because the arcs are congruent, it means that the chords have to be congruent. Congruent chords or congruent arcs have congruent chords. So we know this side of the triangle is congruent to that side of the triangle. We also, looking at this diagram, we know that this segment is congruent to itself. So I'm looking at, is there a way for me to prove these two triangles congruent? And right now I have two pairs of congruent sides. CB is congruent to CB. That B is floating over there. This point is B. So that's reflexive property. Now we need to figure out if there's anything else in these triangles that we know are congruent. One thing we know is that since this is point O, CB has to be a diameter, which means that the arcs CAB and CDB are both semicircles. We can say the measure of arc CAB is 180, and the measure of arc CDB is also 180 by definition of semicircle. I'm going to work with these arcs to show that AC and CD have to be congruent. In order to do that, I'm going to use arc addition postulate. Arc addition postulate allows me to say the measure of arc AC plus the measure of arc AB equals the measure of arc CAB. And the measure of arc CD plus the measure of arc DB equals the measure of arc CDB. AC plus AB equals CAB, CD plus DB equals CDB. That's arc addition postulate. Now, if we look, these sums are equal to the two things that are up here that we said were both equal to 180. So we're going to use substitution property and say the measure of arc AC plus the measure of arc AB equals the measure of arc CD plus the measure of arc DB. Substitution property of equality. Now, I see that on each side of this equation, I have one of the arcs that was given as being congruent. And again, we're just like we did with angle measures and congruent angles, I'm going to let you assume that you can use the fact that if the arcs are congruent, their measures are equal. So what we're going to do is we're going to subtract from each side. And what we're going to get is that the measure of arc AC is equal to the measure of arc CD. Subtraction property of equality. Couple more steps. Now that we know those arcs are congruent, we can go back and use the converse of the theorem that we used up above. If we have congruent arcs, then we have to have congruent chords. So now segment AC is congruent to segment CD. Actually, this is the same way we use the theorem up above. In a circle, congruent arcs have congruent chords. Now these triangles, I have all three pairs of sides congruent. The last part should be quick. Triangle ACB is congruent to triangle DCB by side congruency. And then the angles we want to prove congruent, angle ABC and angle DBC must be congruent. By CPCTC, corresponding parts of congruent triangles are congruent. One last example. It says a plane P cuts sphere O in a circle that has a diameter of 20. What we're talking about here is a sphere, which I'm going to draw as a circle with an equator around it. It's a circle. I can give it a little dimension by going like so. Here's my sphere, and I have a plane that cuts the sphere. Plane being our two-dimensional figure that's going to cut through, not an airplane. For some reason, this always makes people think of airplanes. So think about if you took a knife and sliced through an orange. When a plane cuts through the sphere, what you get is another circle. Here's where the plane intersects the sphere. And it intersects the sphere in a circle that has diameter 20. The diameter of this circle is 20, so its radius is 10. The diameter of the sphere is 30, so the radius of the sphere is 15. The question is, how far is the plane from O? O is the center of the sphere. Distance from the center up to this circle has to be measured on a perpendicular. This is the length that we want to find. We know that the radius of the sphere is 15, so you can draw the radius from this point to anywhere on the surface of the sphere. In this case, the most helpful place to draw it is to the edge of this circle. Now I have a right triangle where the legs are x and 10, and the hypotenuse is 15. This is 225 minus 100, which is 125. I'm going to take the square root of both sides, and I'm going to get square root of 125, which is 5 times 25, so 5 square root of 5 is my answer. Just remember that whenever you're talking about the distance from a point, either to a surface or to a segment, it must be measured on a perpendicular.